Where is the most persistently perilous place on the surface of our planet? Well, let's begin with temperature. Extreme heat and extreme cold can kill within hours, if not minutes. In cold environments, without clothing, the human body by itself doesn't do a very good job of maintaining a high enough temperature to live. It just takes too much work. Even when you feel comfortable and warm, nearly half of your daily caloric intake is used merely to keep your body's temperature where it should be. If you took a human and stripped them naked and put them in an environment at 0 degrees Celsius, they would die from having too cold of an internal temperature within about 20 minutes. We need warmth. But one thing we need more immediately than that is oxygen. And that brings us to the summit of Mount Everest. This place on the surface of Earth has incredibly thin air. At the top of Mount Everest, there is only 1/3 as much breathable oxygen as there is down at sea level. Climbers can endure the conditions for short periods of time if they acclimate for months. But if you were to teleport from wherever you are right now directly to the summit of Everest, you would most likely die within only 2 to 3 minutes because there isn't enough oxygen. Death would come even more quickly if you were at the bottom of the Mariana Trench. There, you would be submerged under nearly 7 miles of water, about 11 kilometers, causing the pressure around your body to exceed 15,000 pounds per square inch. At normal swimming depths, you can always hold your breath, but that far down, with that much pressure, your lungs would collapse immediately. And without oxygen, your brain would go unconscious in 15 seconds and you'd be dead in under 90. You would die pretty much just as quickly as someone who walked into outer space without a suit on. But falling into a molten lake of lava is probably the most spectacular way to go. Contrary to what you see in many movies, your body wouldn't just burn a little bit and slowly sink as if it were in quicksand. Instead, there would be a lot of fireworks. Hot molten lava is liquid rock, 4 times as hot as your oven can ever get. And the human body is mainly made up of water, which, when exposed to that kind of heat, turns into steam explosively. There's a fantastic video right here on YouTube where a guy throws a bag of organic material containing a lot of moisture into hot lava. It doesn't just sink in, it causes a miniature eruption. I highly suggest you go watch it. But what if we want to measure danger not by how quickly you would die, but by the actual total number of fatalities caused? Well, for this, we're going to need to get much, much smaller, like microscopic. In 1918, influenza killed nearly 100 million people, which at the time was 3% of the world's entire population. But places where and when the plague has spread rapidly are even scarier. Between 1347 and 1353, a third of everybody in Europe died because of the bubonic plague, an infection caused by Yersinia pestis. It's easy to think of the plague as something from way back in the past, but it is still here. Of course, now we have antibiotics, which can help in most cases, but believe it or not, in America alone, 5 to 15 people still get the plague every year. In terms of total fatalities, however, the plague and influenza are nothing compared to the danger caused by this guy, Plasmodium. It's a microorganism that can get into our blood because of mosquito bites and causes malaria. Across the totality of human history, the number of deaths attributed to malaria is unbelievable. Researchers like Nobel laureate Baruch Blumberg have studied the history of the human genome and human migration and determined that of all the humans who have ever existed, it is likely that half died from malaria. So, in terms of total fatalities across all of human history, a place where Plasmodium could enter the bloodstream because of a mosquito bite, statistically speaking, could be called the most dangerous place on Earth. But let's switch gears for a moment and talk about places that are dangerous not because of Earth or Earth's creatures, well, actually just one specific creature, us. La Orilla is a mining town in Peru where the murder rate is low but pollution is high. The town's smelter emits pollution into the air, and temperature inversions in the atmosphere above the town trap gases within, causing the town to have 85 times more arsenic in its air than is deemed safe. But that's nothing compared to Lake Karachay in Russia. It was named the most polluted spot on Earth by the World Watch Institute on Nuclear Waste. Has incredibly thin, perilous place on the surface of our planet. We die within only 2 to 3 minutes because there isn't enough oxygen. Death would come even more quickly if you were at the bottom of the Mariana Trench. There, you would be submerged under nearly 7 miles of water, about 11 kilometers, causing the pressure around your body to exceed 15,000 pounds per square inch. At normal swimming depths, you can always hold your breath, but that far down, with that much pressure, your lungs would collapse immediately, and without oxygen, your brain would go unconscious in 15 seconds and you'd be dead in under 90. You would die pretty much just as quickly as someone who walked into outer space without a suit on. But falling into a molten lake of lava is probably the most spectacular way to go. Contrary to what you see in many movies, your body wouldn't just burn a little bit and slowly sink as if it were in quicksand. Instead, there would be a lot of fireworks. Hot molten lava is liquid rock, 4 times as hot as your oven can ever get. And the human body is mainly made up of water, which when exposed to that kind of heat turns into steam, explosively. There's a fantastic video right here on YouTube where a guy throws a bag of organic material containing a lot of moisture into hot lava. It doesn't just sink in, it causes a miniature eruption. I highly suggest you go watch it. But what if we want to measure danger not by how quickly you would die, but by the actual total number of fatalities caused? Well, for this, we're going to need to get much, much smaller, like microscopic. In 1918, influenza killed nearly 100 million people, which at the time was 3% of the world's entire population. But places where and when the plague has spread rapidly are even scarier. Between 1347 and 1353, a third of everybody in Europe died because of the bubonic plague, an infection caused by Yersinia pestis. It's easy to think of the plague as something from way back in the past, but it is still here. Of course, now we have antibiotics, which can help in most cases, but believe it or not, in America alone, 5 to 15 people still get the plague every year. In terms of total fatalities, however, the plague and influenza are nothing compared to the danger caused by this guy, Plasmodium. It's a microorganism that can get into our blood because of mosquito bites and causes malaria. Across the totality of human history, the number of deaths attributed to malaria is unbelievable. Researchers like Nobel laureate Baruch Blumberg have studied the history of the human genome and human migration and determined that of all the humans who have ever existed, it is likely that half died from malaria. So in terms of total fatalities across all of human history, a place where Plasmodium could enter the bloodstream because of a mosquito bite, statistically speaking, could be called the most dangerous place on Earth. But let's switch gears for a moment and talk about places that are dangerous not because of Earth or Earth's creatures, well, actually just one specific creature.
What the fuck is our health kit here?
La Orilla is a mining town in Peru where the murder rate is low but pollution is high. The town's smelter emits pollution into the air, and temperature inversions in the atmosphere above the town trap gases within, causing the town to have 85 times more arsenic in its air than is deemed safe. But that's nothing compared to Lake Karachay in Russia. It was named the most polluted spot on Earth by the World Watch Institute on Nuclear Waste. The lake contains so many radioactive pollutants that you can receive a lethal dose of radiation merely by standing for 1 hour near certain parts of the lake. The Global Peace Index ranks countries by how safe they are. It takes into account a number of factors, including crime and political corruption. The safest country, according to the index, is Iceland, and the least safe is Somalia. But for the highest murder rate, you'll have to go to Juarez, Mexico, where out of every 1 million inhabitants, each year, 1,477 of them are murdered. I've always found it amazing just how many serial killers Miami seems to have on the show Dexter. But Miami is a big city, and so despite all those serial killers, its murder rate in the show is not the highest of any fictional town from a TV show. That honor goes to Cabot Cove, the town where Murder, She Wrote occurred. An analysis of Murder, She Wrote episodes revealed 274 murders, but a population in the town of only 3,500, making Cabot Cove's murder rate 1,490 per million inhabitants. Until recently, that number was unmatched by reality. But last year, the city of San Pedro Sula in Honduras
That is so
reported
cool.
a murder rate of 1,588 murders per million inhabitants. Let's conclude by revisiting pollution, specifically the Chernobyl accident, and a certain oxymoronic danger. For 10 days in 1986, radioactive isotopes spilled out of a blazing reactor core, forcing mass evacuations. It's more than 25 years later now, and many parts of the exclusion zone remain incredibly lethal. But without humans there, many parts of the exclusion zone have seen wildlife flourish, especially endangered species, which can go to the exclusion zone, live, reproduce, and be safe from us.
Hi, buddy.
What
They
is this?
managed to ruin a place
Hi.
to the point
Look
at
at
which
this.
it
What is it?
endangered our lives and we had to leave. And in
Is that a
doing
game you're
so,
playing?
we
Or is that a
left
video?
parts of it a
It's a
little
game.
bit
What is this?
safer for
And you're
other
playing it now. What is it?
forms
What is it?
of life.
Yeah, what is that?
You can read more
Is it your
about
graphics
all of
card?
these topics by following links down in the description below. Keep
Are you going
learning,
through
and
dimensions
as
or something?
always, thanks for watching.
Nope. Tony, what is that?
Who your graphics card?
Is my graphics card on fire right now?
I don't know. Games that how the game's supposed to work?
Nope. Not even close.
It's an online game?
Nope. This is Half-Life, remember?
Okay, there's one that we bought. Okay.
Nope, I did not buy this.
What
But I didn't pirate it.
You got it for Christmas or something?
Christmas?
Yeah.
Nope.
How'd you get it?
Guess.
Somebody gave it to you.
Nope.
I don't know. How'd you get it?
Actually, technically, someone gave it to me. It's free on Steam for like 3 months or something. 2
I just want
months.
to make sure that I shut down our internet again.
Yeah.
This is a completely still image, but as your eye reads what I'm saying and jumps from word to word, the paragraph will appear to slightly, just subtly, wave and boil. The illusion is called anomalous motion. It's neat, but to say it's fun is a tautology, because the word illusion literally means to have fun, to mock, to play with. But illusions aren't just fun and games, they also teach us about our brains. Anomalous motion, for instance, demonstrates that our brains process things at different rates and piece by piece. After a saccade, a quick eye movement, higher contrast elements are perceived sooner than lower contrast ones. When arranged in just the right way, this delay is exploited and your visual system only has one explanation. Low contrast parts of the image didn't get processed later because this myelinated machine is wrong, but rather because the image itself must be moving. Akiyoshi Kitaoka's brilliant out of focus causes nearby neurons to disagree about the little slices they each detect. Some see big changes after a saccade, and some see hardly any. This makes it difficult for our brains to calculate and factor in the effect of our own eye movements, so the image itself appears to be moving. But illusions aren't just about moving. They can also be moving. Poignant, significant, practical. They can mean the difference between life and death, like in nature, or during World War I as dazzle paint on ships. This form of camouflage doesn't conceal the object, but rather makes it difficult for an enemy to ascertain its prey's true shape, and thus where it's heading or how fast it's going. In 1955, the Soviet Union displayed their new Bison and Bear long-range bombers at an air show. It looked like they had a lot. Afraid of falling behind, the US ramped up production on their own B-52 bomber. But the whole thing was an illusion. In the Soviets' film of the air show, the same few planes had been flown past the camera multiple times in formations that gave the illusion of them having more bombers than they really did. By the end of the 1950s, the Soviet Union only had about 150 long-range bombers, whereas the Americans, fooled by the illusion, had built nearly 2,000 at a cost of $900 million. Architecture is full of examples of real-world, practical optical illusions. My favorite are Disney castles. They appear huge, but it's forced perspective, a lie. The tops appear further away from us because they are actually quite tiny. Illusions also tell us about ourselves culturally. The Mueller-Lyer illusion is classic. The horizontal lines are all the same length, but the bottom ones appear longer to people from Western cultures familiar with our rules of perspective and man-made straight lines. However, Bushmen from southern Africa and tribespeople from northern Angola or the Ivory Coast aren't fooled at all. Akiyoshi Kitaoka is using optical illusions to discover glaucoma earlier than current techniques can.
How did I kill this guy?
Anamorphic illusions are
Give me your
used
gun.
to save lives. They look weird from any perspective but one, from which they seem to pop out, defying the environment's actual shape. Hoping to remind drivers to always pay attention, traffic safety organizations in West Vancouver, Canada placed a skewed decal on the road. From the right perspective, the perspective of a driver in this case, it becomes a 3D illusion of a child you are about to hit. Slow down. Bruspup has made some incredible examples of the 3D effect such illusions can have. This object? Just an anamorphic projection. Anamorphic illusions have also been used to safely practice political dissent. In 1746, supporters of the Stuart claim to the British throne
How did I do that?
to be quiet about it. It was treasonous. So, sympathizers served things on trays that looked like this. Innocuous enough until only supporters were around, and it was safe for someone to place a reflective goblet or cylinder on the tray, revealing the tray's anamorphic secret, a hidden portrait of their illicit love, Charles Edward Stuart himself. The Encyclopedia Titanica lists descriptions of every body recovered from the Titanic. It's quite macabre. Why was the iceberg not seen until it was too late? And why did the nearest ship, the Californian, not come to the Titanic's rescue sooner? Tragic questions whose answers might be optical illusions. The Titanic was sailing through conditions perfect for mirages. This theory points out that the Titanic sank at the border of the warmer Gulf Stream and the frigid Labrador Current, where the normal case of cooler air at higher altitudes was inverted, a thermal inversion. Now, because the temperature of air affects its index of refraction, a thermal inversion means light bending in atypical ways. If light reaches the eye from higher up than usual, objects can appear to float. Seriously, like this ship off the coast of Australia. A thermal inversion can also render objects completely unrecognizable, hidden within a haze, like this ship, or like an iceberg, or a sinking ship in need of help. The Delbuff illusion may be causing teeth to split and crack more often than they should when dentists drill holes in them. Dr. Robert O'Shea observed 8 practicing dentists and found that they were all drilling holes that were too big, even though they knew the correct size to be drilling. Why? Well, it may be the same reason people eat more food when they're given a bigger plate. Objects appear smaller when enclosed by larger areas. Holes of the same size may appear different sizes on bigger teeth. Dentists may be deciding that correctly sized holes drilled into teeth need to be made larger, not because they do, but because perception is a tricky thing. Illusions affect not only big ships and teeth, but also your future. The end of history illusion is our tendency to think of ourselves today as somehow done. Sure, I went through a lot of personal growth and changes in taste in the past, but today, who I am now, this is pretty much the final me. But that's not true. Studies have consistently shown that people underestimate just how different they will be, say, 10 years in the future, even though they can easily point out how much they've changed since 10 years ago. I like how Daniel Tomasulo puts it. We believe we are going to live, love, and long for where, who, and what we are thinking about right now. But the research says it just ain't so. This, too, is a transient state. Yogi Berra put it even more succinctly. The future ain't what it used to be. Their advice is, don't imagine your future. Look at other people and their experiences instead. Take their advice. Your imagination is just that. Their experiences are actual data. Now, of course, it's not that simple, which brings us to our final illusion, the illusion of control. Named by psychologist Ellen Langer, it's our tendency to believe we control the outcomes of things we demonstrably don't. It can help motivate us to not give up, and in healthy people at a healthy level, it is optimistic self-appraisal. But it's a lie. In one study, traders in the City of London's investment banks were shown a graph of a real-time stock price and given 3 buttons that secretly didn't do anything to affect the price. But they were told the buttons might have an effect. Try them out, see what you can do. Afterwards, the traders were asked to rate how much they felt they had been able to control the stock price with the useless buttons. And it turns out, the traders who reported the greatest sense of control over the stock price were the ones who scored lowest on risk management tests, and in the real world contributed the least to their company's profits, and in terms of salary, made the least money. It's kind of a bummer. The illusion of control is a nice feeling, but sometimes it's fine. Sometimes it even pays handsomely to admit you don't have control.
What?
And as always, thanks for watching.
Yummy, 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 yummy. Obi, gimme. Wiggy, wiggy.
Hey, Vsauce. Michael here. There is an art museum on the moon. Supposedly, we can't be sure until we go back and check, but as the story goes, in 1969, Fred Waldhauer from Bell Laboratories and sculptor Forrest Myers convinced an engineer working on the Apollo 12 lunar lander to hide a itsy-bitsy, roughly 2 by 1 centimeter ceramic tile within the gold blankets wrapped around parts of the spacecraft that would be left on the moon. And etched onto that chip were artworks by famous artists. According to everyone involved, the plan worked. And when the Apollo 12 team left the moon, the wafer was still there. Now, 2 days later, Myers told the New York Times what they had done, and this image of the wafer was published. It contains a Rauschenberg straight line, a Oldenburg drawing of Mickey Mouse. Pretty cool, and the story is likely to be true. If confirmed, that would make this wafer the first and currently only art museum on the moon. But the thumb is covering something. In fact, it's covering Andy Warhol's submission. Why? Well, according to Warhol, all he did was innocently etch his initials on the chip. He stylized them like this. He drew a somewhat funny W for Warhol and then put a line right across here to make this bit look like an A. That's it. It's just his initials. Here's an unobscured view of a replica. That's on the moon right now. I, however, am on Earth in North America, and this is a map of North America, which is cool because if you are in the place you have a map of, well, mathematically, there will always be some point on your map that is directly above the place in the real world
What the fuck
it
does this even
represents.
do?
Always. It doesn't matter how you hold the map. It can be rotated, flipped, even twisted, folded, or crumpled. It is guaranteed by Brouwer's fixed point theorem. A fixed point is anything that goes nowhere after a transformation. Brouwer's theorem tells us that it is impossible to completely mix up a set of points if they are bounded, without holes, and transformed continuously with no cutting or gluing. Without bounds, every point can be mapped somewhere new. Around holes, every point can be mapped somewhere new. And if you cut or glue, every point can be mapped somewhere new. But otherwise, mixing will always fail somewhere. A transformation is continuous if, as the distance between any 2 points reaches 0 in the before state, it also approaches 0 in the after state. Each square of this checkerboard is filled with point-like pixels of a unique color. As we transform it, let's have pixels still within the square they began in glow. Okay, as you can see, no matter how you resize or manipulate the checkerboard, it will always glow somewhere. You cannot get every pixel to be simultaneously outside of its original square, unless you cut or move the whole shape outside of the space it used to fill. Here's a question. Do you think you can completely mix up coffee in a mug by stirring? Well, of course you can. Not. Stirring coffee is a continuous transformation of the coffee and everything stays within the same space. So Brouwer's fixed point theorem applies. No matter how well you try to stir, there will always be, after the liquid has settled, at least one point that you stirred right back to where it was before. A fixed point. To be sure, coffee isn't made out of points, it's made out of molecules, but they're quite tiny and very numerous, so within a degree of error, it'll pretty much hold. Fixed points don't just frustrate your ability to fully mix things, they can also suck you toward them. They can be attractive, like the number 9. Try this. Think of a number with more than one digit and then add up its digits. Now subtract that sum from the original number to get a new number. If you do this over and over and over again until you're left with a single digit number, you will always end up with 9. Every time. Also, notice that any number with 2 or more digits minus the sum of its digits becomes divisible by 9 right away. What's going on here? Well, there's nothing mystical about 9ness in general. Instead, it's just a consequence of how we write numbers. Numbers can be written in all sorts of ways, but the most common, base 10 positional notation, makes the 9 trick work. In this system, a number like 25 doesn't mean 2 and 5, it means 10 2s and 1 5. That's 25. So subtracting out just the positional digits of a number removes one member from each group. The digit you have 1 of completely disappears. The digit you have 10 of goes down to 9 copies. The digit you have 100 of goes down to 99 copies, and so on. So the whole thing becomes a multiple of 9. Attractive fixed points also play a starring role in a famous method for calculating square roots. It's called the Babylonian method. The number you want to find the square root of is called the radicand, and its square root is some number that is equal to the radicand divided by itself. Okay? Now, step 1 of this method is guess. If your guess is lower than the actual answer, the radicand divided by your guess will be larger than the answer, and vice versa. The true answer will always be somewhere in between those two values. So after you guess, take both values and find their average. It'll be a point in between. And now use this value as your guess and keep going. You will converge towards the true square root at a pretty nice speed. The number of correct digits in your approximation will roughly double after every iteration. That's pretty cool, but let's talk about infinity, specifically Aleph numbers. They describe sizes of well-ordered infinities. The smallest is Aleph null, equal to the quantity of integers that there are. But there are literally larger infinities than that. In order of increasing size, they are Aleph 1, Aleph 2, Aleph 3, and so on. Each one is infinite, but refers to a greater number of things than the infinity before. If you tried to pair up Aleph null things with Aleph 1 things, you'd literally run out of Aleph null things first, even though it's endless. You can hear more about Aleph numbers in this video of mine, but here's the thing, there happens to be an Aleph fixed point. Notice that the subscript of each Aleph is equal to the number of infinities less than it. There are none less than Aleph null, 1 less than Aleph 1, 2 less than Aleph 2, and so on. Each next Aleph number is monstrously bigger than the last, but only adds 1 to the growing list of Alephs. Clearly, these rates are so different, they'll never meet up. But they do. Take a look at this number. Aleph, 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 and so on, an endless cascade of Alephs. How many infinities are smaller than this number? Well, look at its subscript. It's an endless cascade of Alephs, just like the number itself. This is an Aleph fixed point, an infinity so large it is equal to the number of infinities smaller than itself. That's cool, but probably my favorite fixed point related thing is the Borsuk-Ulam theorem. It states that at any given moment, there must be at least one pair of points on Earth's surface that are diametrically opposite one another, but nonetheless have the same temperature and atmospheric pressure. Diametrically opposite points on a sphere are called antipodes, and as I've discussed before, if you place a piece of bread on the ground somewhere on Earth and another one on that point's antipode, well, you've made yourself an Earth sandwich. There are sites that help you locate such opposite points on land, but at this moment in history, you'll notice that most points on land are antipodal to water, which makes sense. The Earth's surface is mainly covered with water, but even though we know that, we don't always appreciate just how gigantic the Pacific Ocean is. Maybe because maps tend to cut right along it, dividing its power. But take a look at this. This is the Atlantic Ocean, all right? This is the Pacific Ocean. It's really more of a water hemisphere. The Pacific Ocean is so large, in fact, it contains its own antipodes, meaning there are places in the Pacific Ocean where you could float. And know that even if you dug a hole straight down through the center of the Earth and emerged on the other side, you would still be in the Pacific Ocean. Okay, anyway, back to Borsacola. To see how it works, let's imagine two thermometers on opposite sides of the Earth, A and B. The temperatures they record will probably be different, but if we swap their locations, always keeping them at all times on opposite sides of the planet, their temperature readings will just flip. In order to swap, well, their readings are going to have to cross at least once. No matter how we swap these always antipodal thermometers, a crisscross will have to happen at least once somewhere. Moreover, these fixed points aren't just peppered around the globe willy-nilly. A continuous, unbroken band of them must separate A's region from B's. Why? Well, because if there wasn't such a wall, that would mean there'd be a way to swap them without their readings having to ever meet, which we know can't happen. Okay, next, let's pick a pair of antipodal points on this band and measure atmospheric pressure at both. If they're the same, hey, that's pretty good. Our job is done. But if they're not, we can just swap the barometers along the band. Like with temperature, the pressures they measure swap, so somewhere they will have to have the same value. Even though weather is chaotic and always changing, and even though the other side of the world is very, very far away, there must always be at least two places on opposite ends of the Earth where the temperature and the pressure are the same. This is true, by the way, for any two variables that vary continuously across Earth's surface. 4 is often called a cosmic number. Why? Well, because, try this. Name any number in English, really any at all. Positive, negative, irrational, complex, uninteresting, surreal, infinite, doesn't matter. Now, count the number of letters in its name. This gives you a new number. Count the number of letters in its name and keep going. Eventually, every single time, you will wind up at 4, where you will be stuck looping forever. Side note, if doing something over and over again doesn't produce a different result than just doing it once, the procedure is called idempotent, meaning same power. Taking the absolute value of a number is an idempotent act. Doing it once or doing it a million times gives the same result. Pushing an elevator call button is idempotent. Once pushed, it'll come to you. Pushing it again and again and again and again doesn't make it arrive faster or differently. Anyway, we get stuck at 4 because it's the only number in the English language spelled with the same number of letters as the quantity it represents. About 4 years ago, Reddit user Protocol7 showed that there are no other endless loops except 4, and that while -15 and -17 both contain their absolute value worth of letters, which makes them special to be sure, they obviously aren't spelled with a negative number of letters. 4 is 4, Chunet. There's no escape. The path to it is forced. Oh, fork. It's even on my forearm. Well, I look forward to seeing you again soon. And as always, thanks for watching.
Oh my god, he killed himself, and I died.
I have some exciting news.
Oh wait, no, he didn't.
If you are a parent with young children, or if you are a young child yourself, I have a video over on Sesame Studios that you should check out. Sesame Studios is from the creators of Sesame Street, and it's a great new channel full of